We all think we get gravity. It feels simple. An apple falls, planets circle the sun, it just works. But what if I told you our entire understanding of this fundamental force is, well, just plain wrong, or at least missing a huge piece of the puzzle? An idea that's been hiding in plain sight and could solve the biggest mysteries in the entire universe. Believe it or not, our story starts on a beach, way back in 1885. A physicist named Osborne Reynolds noticed something kind of weird. When you step on wet sand, the sand right around your foot dries up for just a second. Seems totally random, doesn't it? But what if that simple little observation holds the secret to why entire galaxies don't just fly apart? Seriously, stick with me on this. You see, for all its success, our current theory of gravity has some serious ghosts in the machine. To make the numbers work on a cosmic scale, we've had to invent these fudge factors. We call them dark matter and dark energy. They're supposedly 95% of the entire universe, and yet we can't see them, touch them, or detect them in any way. And these aren't just small rounding errors we're talking about. We see galaxies spinning so ridiculously fast they should have ripped themselves to shreds billions of years ago. We see light bending around massive objects in ways that don't quite add up. And after huge galactic collisions, we find these gravitational ghosts, areas where gravity is strong, but there's no matter to be found. These are the puzzles that keep physicists up at night. Okay, so let's go back to that walk on the beach. That strange drying effect has a name. It's called dilatancy. And a fascinating new theory proposes that this exact same principle, just scaled up to the size of the cosmos, could be the key to everything. So what is dilatancy? Well, it's what happens when you put pressure on a pile of little things, like sand grains. Your foot hits the wet sand, right? And you'd think you're compressing it, squishing it down. But you're not. You're actually forcing the sand grains to shift and rearrange, which creates more empty space between them. The water on the surface just gets sucked down into those new gaps. So it's an expansion, not a compression. Kind of wild. All right, now for the big leap. Imagine the vacuum of space isn't totally empty. Imagine it's also a kind of granular medium. This theory says a huge star doesn't warp space-time like Einstein said. Instead, its mass creates stress in the vacuum around it, causing the vacuum itself to expand, to dilate, just like that sand. This makes the vacuum in that area a little bit less dense. And here's the kicker. Light actually travels slower through this less dense patch of space. This completely changes how we think about things like gravitational lensing. If light slows down as it passes by a massive star, it creates what's called a refractive index. In other words, the light path bends. So the starlight isn't bending because space-time is curved. It's bending for the exact same reason a straw looks bent when you stick it in a glass of water. It's just refraction. Okay. But here's the giant, glaring problem. When we actually measure this dilatancy effect in the lab, it's tiny. It's incredibly weak. For it to explain the light bending we see from distant galaxies, the effect in the vacuum would need to be, wait for it, 10,000 times stronger than anything we've ever measured on Earth. That's a huge, seemingly impossible gap. This should be a deal breaker, right? Well, the proposed solution is pretty extraordinary. The theory suggests that the vacuum of space isn't just any old medium. It exists in a really special state, poised right on the absolute edge of a phase transition, what physicists call a jamming point. Think of the exact moment sand in an hourglass gets stuck. The vacuum is just 0.01% away from that critical tipping point, which makes it hypersensitive to any stress. And this isn't just some lucky accident or fine-tuning. It's a really cool concept called self-organized criticality. The classic example is a sand pile. You keep adding one grain of sand at a time. The pile builds itself up until it's in a critical state, where the very next grain could cause a tiny little slip, or it could cause a massive avalanche. The idea is that the universe naturally pushes itself to this knife-edge state and just stays there, making it incredibly responsive to the tiniest push. So, with all that in mind, how does this possibly solve our first big puzzle, the crazy fast spin of galaxies? Remember, this is the #1 reason we even invented dark matter. We needed some invisible halo of mass to provide the extra gravity to hold everything together. So that's the real question, isn't it? How can this idea of a super-sensitive, expanding vacuum possibly account for all that missing pull? can it explain why the stars on the far edges of a galaxy are moving just as fast as the ones near the center, all without a giant halo of invisible stuff? Okay, get this. The crucial idea is that the shape of the object changes the rules of gravity. On the left, you have a star. The stress it creates spreads out in all three dimensions, like an inflating balloon. The force gets weaker by the square of the distance. That's standard, boring old gravity. But on the right, for a flat spinning galaxy, the rotation creates a shear stress that basically squishes the whole effect into a two-dimensional plane. Now, the force spreads out like ripples on a sheet, and it only weakens linearly with distance. The dimension changes. And the result of that one little change, from 3D gravity to 2D gravity, it perfectly, absolutely predicts the flat rotation curves that we actually see in the sky. The ones where a star's speed stays the same no matter how far out it is. The very thing we invented dark matter to explain could just be gravity acting differently in a flat disk. Just, wow, no extra matter needed. So that handles spinning galaxies. But what about the ultimate smoking gun for dark matter? I'm talking about the bullet cluster. It's this famous collision of galaxies where we clearly see gravity pulling things where there's no visible matter. It has always been the poster child for dark matter. To get the new explanation, we need one last concept: plasticity. Just think about bending a paperclip. You bend it a little, it springs right back. That's elastic. But if you bend it too far, you pass its yield point, and it stays bent forever. It holds a permanent memory of the force you applied to it. So, the standard view of the bullet cluster is that when two galaxies collided, their regular matter crashed together, but their invisible dark matter halos just passed right through each other like ghosts. But this new theory says something totally different happened. The stress from that collision was so unbelievably intense that it pushed the vacuum of space past its yield point. It created a permanent deformation, a dent, a scar in the very fabric of the vacuum itself. So what we're actually seeing out there in the bullet cluster isn't some cloud of weird invisible particles at all. We're seeing a memory. It is a ghost dent that was left behind in the vacuum from a cataclysmic event that happened eons ago. The gravity we detect is just lingering in that permanently dented space long after the matter that caused it has gone. Now, as wild as all this sounds, what makes it real science is that it's testable. You see, a good scientific theory can't just be a cool story. It has to be falsifiable. It has to make specific predictions that, if they turn out to be wrong, the whole theory goes in the bin. And this theory has some really clear tests. For one, it predicts a direct link between how thick a galaxy's disk is and how fast its stars rotate. If astronomers look and find no connection, well, the theory's wrong. It also predicts that the ghost dent in the bullet cluster is a static scar. It doesn't change. If we ever see those halos oscillating or breathing, like some particle dark matter theories predict, then this whole dilatancy model is toast. So we're left with this absolutely fascinating, totally provocative possibility that maybe, just maybe, the greatest mysteries in the universe aren't caused by mysterious invisible particles we can't find. Maybe they're caused by the collective behavior of space itself. It's a radical new way of looking at everything, suggesting the key to the entire cosmos might have been hiding all along in the simple physics of taking a walk on the beach.